and welcome to Week 3, Lecture 3 of CO 442642 Graph Theory. Today we'll be talking about list edge coloring. So what is list coloring? We've alluded to this in the assignments, but I'll just formally mention it now. So list coloring is where you have list assignments for colors. So a list assignment L is an assignment of list L of V for every vertex V in V of G for some graph G here. And then we call a list assignment a k-list assignment if the lists have size at least k for all v in V of G. And we say an L coloring is a coloring phi where phi of V is in L of V for all v in V of G. So that is a coloring where the colors are from these lists. So the idea is that vertices will submit list of colors from which they would like to be colored, and we want a coloring from those lists, where again, adjacent vertices will receive different colors. And then to that end, we say a graph G is k-list colorable if G has an L coloring for every k-list assignment L. So here, no matter what list we have, as long as they all have size at least k, then we're saying we have a L coloring, coloring from those lists. So that's k-list colorable, so that's more general than being k-colorable, where all the lists are the same. And then, as we did with colorings and chromatic number, we define the list chromatic number, which will be denoted chi subscript L of G, as the minimum k such that G has an L coloring for every k-list assignment L, or equivalently is k-list colorable. So clearly the list chromatic number has to be larger than the chromatic number, because you could just have a list assignment where all the colors are the same, but this is a bit more general. And now let me maybe make a few remarks about list coloring, which we'll return to also next week for list vertex coloring, but let me say a couple things. So first question, is chi of G equal to chi L of G always? You might naively think that list coloring should be roughly equivalent to coloring, in that you might naively think that the hardest case is when all the lists are the same, the case of coloring. But this is actually not true. So while the intuition isn't quite wrong in that, of course, if all the lists were disjoint, you'd be able to easily color. You can actually end up with harder things. So you might know a well-known proposition that for every integer k at least 0, there exists a bipartite graph G with chi L of G being at least equal to k, so at least k. So bipartite graphs, which have chromatic number 2, can have arbitrarily high list chromatic number. And even more surprisingly, in a theorem by Alon, is that if G has average degree D, then chi L of G is at least omega of log D. So the list chromatic number grows with the average degree, which is very different from how coloring works, as bipartite graphs can have arbitrarily high average degree, but here actually the list chromatic number is kind of tied to average degree, because of course it would be bounded by upper bounded by some function of average degree, namely average degree plus 1 if you take the max average degree, but here it's lower bounded by the log of that. And it's not quite known what the right answers are there. So that's one. What about for edge coloring? Well, you can define the list chromatic index, denoted chi prime L of G, to be the chi L of LG, so the list chromatic number of the line graph. And I should mention that the list chromatic number has a number of alternative names, such as choosability or choice number, which have now kind of fallen out of fashion. And so similarly, these can be, edge choice number or edge choosability. But here we'll just use list chromatic index in keeping with this list chromatic number that we'll be using for list coloring. And then what? Well, here's the big conjecture. It's quite surprising. This is called the List Coloring Conjecture. It's proposed by at least 6 and probably more various authors from the 1970s and early 80s. And it says if G is a graph, then chi prime L of G is equal to chi prime of G. So it posits that for edge coloring, chromatic number and list chromatic number are always equal. That for edge coloring, coloring and list coloring are equivalent. There's just something special about line graphs where it doesn't make any difference, where the hardest case really is having all the lists the same. So even though that's not true in general, the big conjecture is this does work for edge coloring. Okay, so maybe let's talk about what's known about the list coloring conjecture. Right, so if we could prove this, we'd have solved all of list edge coloring, right? Well, what is known So after being bandied around in the 70s and 80s, Galvin in 1995 proved that if G is a bipartite graph, then they are indeed equal. And I'll go through a proof of this in a bit. It's remarkable, it's nice, it's short. It's a very nice result. So it's true for bipartite graphs. What else was known? Well, the next year, Kahn in 96 proved the conjecture asymptotically. So he proved that if G is a graph, then chi prime L of G is 1 plus little o1 chi prime of G. And I'll say a little bit about that at the end, but that proof is much longer and uses probabilistic methods. But a very nice result. So we know the list coloring conjecture for bipartite graphs, and we know it holds asymptotically. So as you go off to infinity, you get smaller and smaller error to get closer and closer to being it. However, it doesn't, with Kahn's result, we can't actually prove it equally. It doesn't hold even for large enough delta, as we saw with Reed's. It's really saying there's a bit of an error term, and I'll return to that. But we know it holds asymptotically, and we know it actually holds for bipartite graphs. Very nice results. So let's go through Galvin's theorem, but let me first say a couple words about what it really means. So you might understand or be familiar with this, but maybe you're not. So maybe you've heard of a Latin square. A Latin square is an n by n array such that each of the numbers 1 to n, say, appear exactly once in each row and exactly once in each column. So in each row you have the numbers 1 to n, in each column you have the numbers 1 to n, each square getting one of these numbers. And so that's been around since at least the 50s, but actually this is just equivalent to a Latin square as an n-edge coloring of k and n. All right, so because what you're really doing is k and n, you can view the edges of k and n as rows and columns, and to rows or columns that you have incidency with the squares of the rows and columns. And so then having these constraints on each one in each row, one in each column, exactly corresponds to having a proper edge coloring with the colors 1 up to n. And well, then we know by what we did last class with or 2 classes ago by Koenig's theorem, that since you're bipartite, chi prime k and n is equal to delta k and n, which is of course n. So Koenig's theorem would suffice. I mean, you could also just maybe directly do it for complete graphs, but you could use Koenig's to give a proof that these always exist, these Latin squares. And maybe then interestingly was this conjecture of Dinitz in 1978. It goes like this. Given an n by n array and an assignment of n symbols to each square. So for instead of the numbers 1 to n, let's say that each square has its own private symbols that it wants to be colored. Now those can overlap, but each one chooses a set of n symbols from which it wants to be assigned a symbol. Then the conjecture is that there exists a choice of symbol for each square, such that each symbol appears at most once in each row and in each column. So this would be Latin squares if all the sets of symbols were 1 to n, but maybe they're allowed different ones. And if you think about that, that's exactly asking the question, does the list chromatic index of k and n equal n? But no matter what lists of symbols I have for these squares, these edges in k and n, then you can actually color. So really, this is a very nice question, right? The list coloring conjecture for bipartite graphs, for k and n in particular, can we always kind of get these generalized Latin squares no matter the list assignment? And as already hinted, this is obviously then true by Galvin's theorem. So now we'll go on to a proof of Galvin's. So how do we actually prove for k and n, and even more generally for all bipartite graphs, that you can actually always get a list coloring as long as the lists have size delta? Well, to do that, we'll introduce a new method called kernels and kernel perfection. So a kernel will be a kernel of a digraph D. So here we're going to be doing digraphs. That's directed graphs, where you directed the edges. So a kernel of a digraph D is an independent set U, such that every vertex in D minus U has an out neighbor in U. So here's a picture. So say this is your digraph D, then kernel U, as the blue set, would be an independent set, but has the property that every vertex outside has an out neighbor, so has some neighbor in U, which is then directed towards you. So that's what we call a kernel. So you have this independent set, and everybody outside has an out neighbor in the set. So what good is that? Well, we can define something called kernel perfect. So we say an orientation D of a graph G is kernel perfect if every induced subgraph D prime of D has a kernel. So what do we mean? Well, we've given a graph G. An orientation is one in which you just actually direct the edges to make a digraph. And we're saying if whenever you take an induced subgraph, so induced, remember, deleting only vertices, not edges, the resulting thing has a kernel. So it seems a bit strange. What good is that? This kernel perfect? Well, it's key. We can actually prove a very nice lemma, which I'll call the kernel perfect lemma, relating list colorings and kernel perfect orientations. How does this go? We'll let G be a graph and L a list assignment of G. If G has a kernel perfect orientation D, such that the size of the list of every vertex V is always strictly greater than the out degree of V in the orientation, then G has an L coloring. So it's a little strange, but maybe that should seem reminiscent kind of greedy. If you could actually take orderings of the vertices and direct edges that way, then that would actually be kernel perfect if you think about it, and then we're kind of generalizing greedy here. So this lemma would tell you then greedy would work, but actually this generalizes greedy because maybe the orientations are allowed to have actually directed cycles as well, and don't have to come from orderings. So given this kernel perfect orientation, we need to produce the coloring. So let me prove this. So proof, you go by induction on V of G. If V is empty, V is 0, then there's nothing to show. You just take an empty coloring. Okay, then what? Well, here's the trick. So where do you go from here? Well, you know you're not an empty graph, so there's a vertex. Pick any color from the list of that vertex. So really just pick a color that's in the list somewhere. So the V won't actually matter, just the color. So I pick this color alpha, and I look at the subgraph induced by all the vertices colored, have alpha in their list. So I take D prime, that should say G of that, but take the induced subgraph on that set of vertices. And then what? Then, well, since D is kernel perfect, D prime has a kernel U. Right, this is the guarantee that whenever you take an induced subgraph, so if you just restrict the ones with color alpha on the list, you're guaranteed a kernel. What good is that? Well, now color everybody in the kernel with the color alpha. We can do that, right? It's good for coloring because it's an independent set. Then what? Well, we've used it on those vertices, so we should remove the color from everyone else. Why? Because everyone outside of D prime doesn't have alpha anyway, so you don't have to remove it. But everyone inside D prime has a neighbor, in particular an out neighbor, in U, so of course you should remove it if you want to get a proper coloring. So we do that, and then do you see what happens? Well, what happens to the list sizes? Outside of D prime, they don't change, so that's good, because then they still satisfy the condition that they're greater than the out degree, because we're just deleting some vertices. We're going to delete the vertices of U, because we've already colored them, and see if we satisfy the condition. So that works for the ones outside D prime, but it also works for the ones in D prime. So how do we get this? Because, well, yes, I lost the color alpha. Of course I had to lose alpha because we removed it from the rest of D prime, but I also am guaranteed to lose one out neighbor because of the kernel perfection. That was the definition of kernel. So we always guaranteed to lose a color, but we're always guaranteed to lose at least one out neighbor, and we preserve this fact that the list sizes are greater than the out degrees. So then by induction, G minus U has an L prime coloring, and hence G has an L coloring. You just add back U, which was colored with alpha. So you kind of inductively pull out kernels, coloring them with the colors. So you take kernels of colors, and you inductively color in this way. That's very nice. It's called the kernel perfect lemma. And then what do we do with that? Well, now I can prove Galvins theorem to you. So let me go ahead and prove Galvins theorem. How do we start? Well, let G equal AB, so let me name the sides of this bipartite graph, and let K, that'll be the number of colors, be chi prime of G, which is delta of G, of course. And our goal here is going to be to find L colorings from K list assignments L. How do we do that? This is the weird part. Maybe for K and N you think, okay, we could use the information, but for general bipartite graphs, we don't have any information really about the graph. So we're going to use the fact that we know it has a coloring, right? Since K is chi prime of G, let phi be a K edge coloring of G. So we're going to use this coloring, this actual proper, ordinary coloring in a clever way to get a kernel perfect orientation to then use the kernel perfect lemma. How does this go? Well, here's the orientation I'm going to build. Let D be an orientation of the line graph where, again, we're doing coloring the line graph, so you actually want to orient the line graph. So it's a little bit weird, but so what does that mean? If I have two edges in the original graph, right, that are incident with each other, E is, incident with E prime, I want to orient that somehow, that edge in the line graph. How do we do this? Well, let's assume that the color of E is strictly less than the color of E. That should read E prime, phi of E prime. How do you do that then? What kind of orientation? Well, from E prime, we'll direct it from E prime towards E if E intersect E prime is in A, and from E towards E prime if E intersect E prime is in B. So here's a picture of how this works. We have A, we have B, and let's say we have some edge coloring. So here my green edges are colored 1, my blue edge colored 2, and my red edges are colored 3. And then what we're doing is, for each pair of incident edges, we're putting kind of a direction. So on the vertices in A, you're directing towards smaller colors, right? So the blue-green edge incidence there in the middle is directed from blue to green, from 2 to 1. And you have a direction from 3 to 2 and from 3 to 1 in these pairs of edges. And the same on the other side, but reversed. So there, the 1 directs to the 2, 2 to 3, and 1 to 3 at that vertex that's incident on the right side. So that's our orientation. Now we just have to show that this orientation satisfies the conditions of the kernel perfect lemma. So let's think through that. Well, let me have an edge E. Let's call it UV, where U is in A and V is in B. And let's have the color of E be I, for some I between 1 and K. Then what's the out degree of this edge E? So think about the out degree. So maybe go back to the old picture, like look at the edge 2 in the middle there. What's its out degree? Well, for the edges incident near U, its end in A, you're going to find that you only go to smaller colors, while for the ones around B, you go to larger colors. So what this means is the ones around U, as written, you count the number of ones with smaller colors, and for the other side, you count the ones around V with larger colors. And what is this? Well, remember you have a coloring. Right? So around a vertex, there can only be at most one edge of any given color. So what does that mean? Around U, how can you have smaller colors? Well, you have colors 1 up to I minus 1 maybe, so there can be at most I minus 1 for that first term. Similarly, on the other side, you can have at most K, you can have at most I plus 1 up to K, which would be delta minus I, or which then if you put in, you sum up these two, you get a bound of delta minus 1, or rather K minus 1 equivalently. So the out degree of any edge in that picture is always at most K minus 1, is this max degree minus 1. So not, because it's not incident with any edge colored itself, its own color. So this is very tricky and nice. So we've done that part. You see, we've established that the out degree is always strictly smaller than the list sizes, which were K. Then what do we do? Well, now we just have to prove that this is kernel perfect. So we check the degree condition, and then you check the kernel perfection. So let D prime be an induced subgraph of D, and then it turns out D actually has a kernel. And this is actually because of a well-known thing, the stable matching marriage theorem. So what is this? Well, if you think about it, a stable matching will be, if we set up the preferences right, actually exactly a kernel. So wherein it'll be a matching, so there'll be an independent set in the line graph, and actually by the stability will mean that everyone outside will have a direction in. So how do we do this? Well, we use preferences where a vertex V prefers a neighbor U to a neighbor U prime if U prime V, that edge, is directed towards UV. Right? So that was, I won't go again through the definition of stable matching. You can look at D still and the proof of the stable marriage theorem, which is very nice and classical, but actually, this is exactly what we need to show a kernel. So I won't bother to go through the details of that, but that's exactly what we get. A stable matching is independent set, and every other edge outside can't get to the, has to have an out neighbor into the matching, must have some pair that's more preferred. Okay, so then what? Well, then we're done, right? Hence D is kernel perfect, and by the kernel perfect lemma, it follows that the line graph has an L coloring for any K-list assignment L, and so the list chromatic number of bipartite graphs is actually delta is K, which is the chromatic index as well. So that was the proof of Galvins Theorem, so maybe meditate on that. Again, you can read the full proof in D still in section 5.4. but I'm going to continue on now and just say a little bit about Kahn's theorem in the time we have left. So again, what was Kahn's theorem? So Galvin's was for bipartite graphs. This is asymptotics for Kahn. He says that actually the list chromatic index is asymptotically equal to chi prime of G. And I'll just mention a couple of the proof ideas. And they're nice and they use probabilistic methods, which we'll get around to later in the term, though we won't do this theorem in this class. But here's roughly the idea. You randomly color edges. You're trying to color, say, from roughly delta colors, you randomly color each edge. So for each edge, uniformly at random, picks a color from 1 up to k, where k is the number of colors we're using. Now this won't create a coloring. Of course, there might be conflicts. So you uncolor incident edges that have the same color. So if 2 edges around a vertex both get colored 1, let's just uncolor it. So this won't produce then at least that will make the coloring proper, but it's only going to be partial then. So what do? We iterate. So this is very nice. We just keep iterating these kind of random coloring procedures, and we use some probabilistic properties to show that there's always at least a chance in each step that we do a pretty decent job at coloring, and then we show that we can keep iterating, keep preserving those properties, and end up actually coloring most of the graph. That won't finish everything, but you can actually finish if at the original step you chose a reservoir, like each edge or vertex kind of has a reservoir of colors from which we'll end up finishing. So this is, a 20-30 page proof. I can't do all the details in 2 minutes here, but that just gives you some flavor. So where Galvin's is nicely from these kernel perfection, which these very structural techniques, Kahn's is actually from probabilistic methods. And I should note that Malloy and Reed, a bit after Kahn, were able to improve the error term. So Kahn just kind of showed your 1 plus little o1. Malloy and Reed actually showed that your delta plus something on the order of square root delta, say log to the 4th delta. So square root delta, polylog delta, which is still the best known bound to this day. So we haven't proven delta plus 1, but we've proven kind of delta plus on the order of something like root delta. And I should also mention that Kahn actually proved his theorem for hypergraphs, at least for linear hypergraphs. So I won't get into that here, maybe we can come back around to it later, but it actually holds when edge coloring what's called k-uniform linear hypergraphs. So where the edges have sets of size k instead of 2 as you have for graphs. And a hypergraph is linear if any 2 vertices are contained in at most 1 hyperedge. So that's kind of, for hypergraphs, the equivalent of being a simple graph. So he actually extended that to edge coloring linear hypergraphs, k-uniform linear hypergraphs. So that's about where we'll stop. So we've talked about list coloring, but maybe this actually leads into our next lecture where we'll be talking not about list edge coloring, but actually what happens when you want to color multigraphs. So we can do some very nice things when the graphs are simple, or even hypergraphs are simple here, but what about when we want to edge color multigraphs? That also makes sense, but what is known and what's conjectured there? So until next time, see you then.